Hi everyone, I'm Igor. I'm the Rust engineer at Zircuit, and today I'm going to share with you the modular architecture of our modular prover. So to get started, I'm going to start with who Zircuit is, and if you haven't heard about us, some case. Then I'm going to talk about the problem, what led us to do this modular architecture in the first place. Then I'm going to talk about the fast evolving landscape of proving systems, which is one of the reasons why led us to do this in the first place. Then I'm going to talk about the idea why behind the modular architecture. And then they're going to go through in detail about the modular architecture itself, and then some closing thoughts. So who are we? So we are Zircuit, and we are ZK EVM built on Hello 2 for now. Soon we're going to drop that E. We're going to become ZKVM. We are trying to shop around for some implementations for that, but soon enough we're gonna drop the Halo 2 and become ZKVM. We have our main differentiator is security at the sequencer level. I'm happy to talk more about the ZKVM and this after the talk. We are secure native bridge, and we are VM compatible, and all of that we bring that together with the modular architecture, which is what I'm going to be sharing with you today. So the problem. So here I'm going to go with an example just to highlight like what the problem is. So let's imagine we have a proving pipeline, and in the prover we have a few components, right? We have a witness mapping, we have ZK EVM circuits, proof system, and aggregation scheme. Doesn't really matter who they are, but what I want to highlight is here these components are attached directly to the pipeline. And for instance, witness mapping is attached to witness loading. The ZK EVM circuits attached to ZK EVM provers, the proof system to the verifier, and the aggregation scheme to the aggregation prover. And the problem here, say I want to bring I want to update them to new components, or I want to bring two new components to the system, right? And in this case, I want to bring a new witness mapping and a new proof system, right? The problem with that, with this architecture, is that things start to break, right? All those change there, those components, I would say glue code. You find yourself not only updating the new system, but also all the systems, because all of those are tightly coupled together, so that becomes a problem. So the problem, right? So ZK research advances very, very rapidly these days, becoming obsolete in about 3 to 6 months. We have a lot of ZK VM. If you look at Zisk, OpenVM, all these days, God knows what's going to happen in the next month or so. So if you have a tightly coupled system or a very tight system, then you become obsolete very fast. And what exactly that? If you have a very tight topology and you find yourself like trying to fix all this glue code, and by the time you finish, you're going to be very behind when all the things come out. And that's where you are, right? Instead of updating your current system, you're always playing catch up instead of working on top of them. So before I go into the actual modular prover, I just want to highlight how these systems are fast evolving. So in 85, right, we have the interactive zero knowledge proofs come, and then in the 90s, non-interactive zero knowledge. And then in 2011, ZK Snarks, 2013, Pinnacle Protocol. Then Gross 16, 2016, Bulletproof 18, ZK Starks, Splunk, Halo 2, 2019, ZK VMs, and then 2021 Plunky 2, Halo 2, 2021, and then 2022 Plunkish, last year SP1, this year we have SP1 Turbo, Risk Zero, and then last week we had Zisk come up with something super cool, so very fast, and God knows what's going to happen next year, right? So if we don't have a modular architecture that can support, new proving systems, which is going to we're going to end up something like that, we end up like that kid trying to catch the ball when you're never going to be able to, because it doesn't have the capabilities or the skills to do so. So we want to avoid that. So how can we develop a modular architecture, right, that allows efficient integration, rapid technological advancements without minimizing integration costs, right? That's what we are going after here. So the idea behind all of this is design for change, right? The design for change is instead of design for a specific technology, you want to design for something that's going to change in the future, right? It's going to change in the next 2 months, 3 months. You don't know, so you want to design with change in mind. Something that's going to be easy to snap in, snap out, right? You don't want to because you go remove a component and introduce a new component, you don't want to update the other components. You want to do exactly that, snap in, snap out. It's low coupling and high cohesion, meaning the components have specific responsibilities. They only do one thing alone, and then there's no ambiguity on those components. And those components are extensible and scalable. The system can scale or up or down depending on the inputs, and you can actually customize how you do that. So that's the idea behind it. So now let's try to get this tight architecture and try to come up with something that a little bit more flexible, let's say. So let's start by removing all those breaking changes or the chains. And now the idea is let's introduce like an abstraction layer, right? Or in this case, we call the business logic. Now, instead of attaching the components themselves to the pipeline, we want to attach this business logic abstraction layer to the pipeline, right? So instead of the components being attached to the pipeline, now we have that abstraction layer. So now instead, the components is going to be following this abstraction layer we call trace because everything is in Rust that what we do now. And as long as those components follow the business logic, the pipeline should work since that pipeline is attached to the business logic. So now let's go into what that really means in the Zircuit modular architecture. So everything is modeled under the modular prover. We actually do have two assumptions. The prover that you're trying to implement can prove and can verify, which is pretty much 99 or 100% of the provers today, right? So we make those assumptions, and they have some components, KVM, VM, doesn't really matter as long as it can prove, it can verify. The modular prover support that architecture. And then we have the modular orchestrator, which is responsible for sending the message between those components. Maybe you have a prove, maybe you have an aggregation layer, maybe you have sending those messages to the L1. And that's the responsibility of the modular orchestrator. Maybe you want to store the intermediate components into database or in the cloud. So that's responsibility of the orchestrator. And we have this test framework, which is not only a testing framework, which can test the modular prover and the modular orchestrator. And you can also measure CPU and memory. That way you don't have to implement everything from scratch. You can test things from end-to-end or parts of the system with this testing framework. Cool, so here I have an example where on the left we have something what we had before, the tight couple system, and on the right is an example of what it looks like now. So just for this example, we have the same components there, but again, instead of those components being directly attached to the pipeline, those components are attached to this business logic, which is called traits because there's that interface used in Rust, and that's what's attached to the pipeline. And the nice thing about this is that as long as those components follow those traits, right, you implement, or maybe the prover needs to prove, needs to verify, as long as you bring that component and you implement those traits for that, you can do exactly that. Just plug that in. You don't need to update anything else, and the pipe you shouldn't need to update glue code and all that, and everything else works good. And the good thing about that, we don't. Instead of spending months and bringing a new component, a new proving system, we can spend a few weeks actually making that work, and then the other weeks, the other months, actually optimizing the existing system and making it a little bit better instead of playing catch up. Now the modular orchestrator. The modular orchestrator was constructed with this dispatcher and collector paradigm, where the dispatcher is this expects one input, generates one output, and the collector expects multiple inputs, can generate one or more output, and they do something with it and then generate something. And then nice thing about this is the message between them is all taken care of. You just need to define where it's coming from, where it's going to. And you can define like where you want to store intermediate steps, like maybe you want to store in memory or local storage or in the cloud, and also that's taken care for you, which is pretty cool. So let's go through an example, right? So let's say I have an execution client, maybe Geth, Bezu, Reth, doesn't really matter. And this execution client is generating some blocks, traces, or data in this case. And the first layer, I have a layer of proof. Maybe you have circuit proofs, maybe a ZKVM proof there. And then after that goes to another queue, and I want to aggregate, and I want to store the intermediate steps in the local database, right? So here, the proof, since it expects one input, generates one output, that becomes a dispatcher. And the aggregation becomes a collection when you think about the modular orchestrator, like that. And similarly, if I have another example here, but in this case, say I want to, instead of aggregate right after proving, I want to do a compression layer, right? Which is kind of something what we do. We have another compression layer there right now, but just for simplicity, say we have another example like this, and instead of storing the intermediate steps in the local storage, we want to store in the cloud. And similarly, the both of the proofs there, they become dispatchers, since they expect one put generates one output, and the aggregation there becomes a collector. So that's the idea, and you see soon enough that the queues pretty much go away. You don't have to worry about implementing that yourself, because that's taken care of by the modular orchestrator for you. So to go a little bit more detail on the dispatcher collector, right? So the dispatcher, as I said before, expects one input and one output, and it has this processor, which takes the input, does something with the input, right, and generates an output. We just happen to have a proof system, and this something is actually the proof itself, which is the executable. Can be a Rust executable, can be a binary, can be anything. It doesn't really care as long as it does something. And the collector is same thing. You define the input, define where it's going to, the output, destination. And instead of defining the executable or processor, you define a collection strategy, right? Like, since you're getting multiple inputs, you want to put that into a chunk, something where maybe you want to collect based on number of inputs, maybe you want to collect based on how much input your circuits can support, right? Which is our case. And maybe you want your own custom strategy, right? And that's also supported, and you can define that. And again, as long as you define your input and your output, that collects for you. Okay, so next, yes, let's take a closer look at this example. So I just wanted to simplify this, right? This is the very first example, so this becomes something like this, right? And here I purposely removed the queues, because you don't have to worry about that. As long as you define where it's coming from, in this case, the proofs there, the input is coming from the execution client, and from the collector is coming from the dispatcher. As long as you define where it's coming to, the message bus takes care for you, right? You don't have to worry about implement your own NAT system or anything like that. And again, the storage, maybe you want to store that in the intermediate steps, memory, local storage, cloud, or doesn't matter. That's also taken care for you. And similarly, the second example is going to be very similar, but instead it's going to have two layers of proving, right? The proof, compression, and then aggregation, and again, the message bus and storage, all there handling, the orchestrator handling for you. And for our use case, right now we have a few layers of that for our current case, but soon we're going to be ZKVM, and I think it's going to be just one layer of proving, maybe one layer of aggregation, but we're still working on that. Cool. So and then how is this any better than what we had before, right? So just to highlight a little bit more, So again, let's say on the left, we have this tightly coupled system and we want to modify two of the systems, right? If we do that, right, things start to break. Then you have to update your witness mapping, then you have to update some of the pipelines here and there, then you find yourself like spending a lot of time updating this glue code. But on the right, if you do exactly the same, right, you want to update the proof system, maybe the aggregation scheme, you have to do exactly that. As long as those components follow the business logic, the traits, the abstraction layer, then you don't have to worry about updating anything else. Everything just falls into place. And maybe I'm running out of time, I believe, so I'm gonna go quick on this one. So the testing framework is configurable, modular, automated, and the nice thing about this one is have built-in capabilities, meaning you can use the same testing framework to run like how much memory is using, how much CPU, and that way you can test different topologies to see like which one works best for you, which one is faster, which one aggregates more, which I guess which one is going to give you more TPS or faster finalization time, I guess. And you can use the same framework for both. So if you want to put it all together, so, right? So let's say tomorrow there's a new proving system, I want to bring it in, right? So I use choose the proving system first, right? Then I use the modular prover to implement the abstraction layer first, like the prover and the verifier mostly. And then I use the orchestrator to come up with a topology, right? Maybe I want to have a proving layer, then I have a couple compression, or then aggregation. Then again, you can choose however you want there. And then you can use the test framework to test different topologies, see which one is faster, which one is works best for your use case. And then using that, you choose your best topology and ship it. So some closing thoughts. So you want to actually scale collectors, because when you think about collection strategies, right? Like you want to collect based on number of inputs, maybe you want to collect based on, you have your own use case. It's not that easy to abstract away this collection strategy and decentralize, if you will, because how do you deal with like multiple collectors receiving the same input? You don't want multiple collectors doing the duplicate work, and you don't want them to messing up with each collector, and yeah, so it becomes a little bit hard to think when you want to scale collectors. We want to learn hardware through dispatch collect paradigm and facilitate distributed proving. As you can imagine, you have some clients that has some more powerful machines. They can run that prover for us, and that way we can not run everything in house, and you can have like proof of proof instead of proof of work, if you will. So some takeaways, it's very hard to keep up with ZK research, right? They come and go very fast. That's why we have this modular architecture. So we found a way to abstract away the proving system and the orchestration, which makes us a little bit more agile when adopting a new proving system. And we just happen to have to roll up and the nice thing about dispatch collect, you can use for anything as long as you have an executable or something that collects, and we just happen to have a proving system that way. And that's it. I think I have a couple questions. 1 minute, 1 or 2 minutes for questions.
Why are you moving from Halo to? Take Zoom, please.
Sorry?
Why are you moving from Halo to?
Oh, well, these days the buzzword is ZK VMs, right? And also to Halo 2, whenever there's a new something that we need to modify the circuits is really painful, and debugging circuits is very painful, and so it's just gonna make us more agile and faster. Also, like I think we're looking to SP1, risk 0, and once we move there, all we need to worry is the actual orchestration, because the proving system is pretty much like a Rust program, right? Instead of worrying about circuits, so that's become much easier to maintain as opposed to circuits themselves.
Okay, thank you. You can please continue outside if you have more questions. We're out of time. Thank you.